Hello, everybody. I feel like I'm in a nightclub here with all this darkness and lights going on. So, my name is Moa. I work at Chalmers University in Gothenburg in Sweden, where I do the things that academics do. I teach students, I do research, and so on. And in this talk, I will give a brief history of computer mathematics and how it came to influence the development of several programming languages. Most notably the early functional programming languages like standard ML, but also Lisp. And this is a history of AI in parts, so I'm not going to talk about neural networks or machine learning or some of the very, very trendy things that almost become synonymous with AI today. But I think it's important not to forget that AI is more than that. So intelligence is also about doing reasoning, for instance, in mathematics. As well as being creative. So that's what I'm hoping to talk about today. I will first give a brief history, and then I will talk a little bit about my own research and do some live demos. OK, but let's start. So I'm going to go back not quite to Wittgenstein, as one of the previous speakers, but to the 1950s and the birth of AI. So solving mathematical problems was, in fact, one of the very first tasks that was addressed by the very earliest AI systems. And one of the first programs was called the Logic Theorist, and it proved theorems about propositional logic from Russell and Whitehead's famous book, Principia Mathematica. Russell, that's Bertrand Russell, who was supervising Wittgenstein, by the way. And this program was written by two guys called Alan Newell and Herbert Simon. And it was presented at a very famous conference called the Dartmouth Conference in 1956. Which was organized by a guy called John McCarthy, who was considered actually having named the field artificial intelligence. So a lot of very influential people were here. Newell and Simon, just to mention, they were later to be awarding the Turing Award for their contribution to AI. And Simon, he also won the Nobel Prize in Economics. So it was smart people kicking off this work. Anyway, to implement this program that was reasoning about mathematics, they were doing reasoning as search. So basically, by today's standard, maybe we wouldn't say that this is very intelligent, but you had a bunch of rules that you could apply to take steps in the proof, much like a game, and some heuristics, rule of thumb, which would guide you in doing this kind of search. And they had to invent programming language for dealing with this, doing this reasoning as search, and processing lists of options. And that programming language was called IPL, and it was actually an early predecessor to what would later develop into Lisp, which has influenced Clojure, I believe. Well, in what sense was this program intelligent? So a quote from this paper here says that, well, the program in this LT, logic theorist system, it doesn't change its source code as it accumulates experience in solving problems. But it does learn in one respect, which is quite different from what we mean today, namely that it stores the theorems that it proves, and these theorems are then available as building blocks as we do subsequent proofs. That might sound obvious, but it was quite revolutionary for a computer program to do this kind of things. So it accumulated knowledge, and then which it then could use. OK. So AI was kicking off. In the 1960s, there was major optimism. It was a hype, a bit like today, actually. So, a lot of problems would be solved within 10 years. So for instance, Newell and Simon, they said that within 10 years, a digital computer will discover and prove an important new mathematical theorem. We were also going to have machine translation, all sorts of wonderful things that were only, we're approaching some of those things today with the help of big data and machine learning, but some things are still unsolved. Nevertheless, there was a lot of development, and research into AI for mathematics grew into a little bit of a subfield of its own called automated reasoning. There was some famous and very important algorithms being developed during the 60s, which are still the kind of bread and butter for automated reasoning systems today. One was called DPLL. It's the initials of the people who invented the algorithm. And it does SAT solving, which is satisfiability solving, if you heard about that. So that's reasoning in propositional logic. So you only have variables can only be of type Boolean, we could say. And also an algorithm called resolution for a little bit more of an advanced language or logic, if you want, first-order logic. Where you could have things like saying, for all students will pass the course, and things like that, or there exists at least one student who will fail the course. But you couldn't have things like, it's called first order, because you can't have this quantifier and say, for all functions. So you can't have functions like map or fold that you know from functional programming language. Anyway, basically, these provers still worked by this paradigm developed in the 50s, so reasoning as search. So you feed the theorem prover axioms and a conjecture, and it's kind of a black box, and it does its search, and then it spits out and says, yes, I proved it, or no, I didn't prove it. However, once you start trying to prove something that's slightly more complicated, turns out that the search space, the number of options, if you're playing this game of proving mathematical statements, it grew very, very large. So the computers of the day, they couldn't really handle anything very complicated. So that was a bit of a downer for this optimism early on. So, well, in the 70s, it became apparent that all that was promised in the 60s wasn't going to happen. So there had been, if we look at mathematics, there had been no discovery of important new theorems. There was no machine translation. There was no reliable image recognition. So in particular, in computer mathematics, it was either you could do automatic proofs, but it was really slow, and it just said yes and no. It didn't really tell you why, or it wasn't really, a human couldn't really understand what it had done. So the other thing that people tried to work on was proof checkers, where a human had to kind of program the proof in every little detail, and then you could have, well, a computer looking at the result and try to make sure that you hadn't made any mistakes. But there was no automation, and mathematicians to this day don't like to program their proofs. They just want to write them down. So this is sometimes referred to as the AI winter, and a lot of funding was drying up for AI. However, in some places, some people still carried on. For instance, in Edinburgh, which, by the way, is where I went to university. In the 1970s, there was some researchers in Edinburgh that thought, OK, well, we can't have full automation, and it's really boring to just check everything. But can we do some sort of combination? So maybe we can have an interactive mathematical system where the human does some parts and the computer checks that it's it's okay. So this was implemented in a system called Edinburgh LCF by a guy called Robin Milner, who has made many important contributions to computer science. Well, he introduced the idea of tactics. So tactics are these kind of small programs that automate parts of mathematical proofs and can be combined. And in addition to the steps that are too complicated for the computer to do, the human can sort of program and the computer checks them. And this way you can sort of build up theories of theorems and their proofs. So coming back to this idea in the 1950s that the prover should accumulate knowledge, which it can use in later proof, is very much present here as well. So you build up your theories, and then you can do richer reasoning. Okay. So how would we implement all this? Well, it turned out that we need higher order functions. So back when we just wanted to do reasoning as search, we needed list and list processing, and they invented something like Lisp. Here we need higher order functions like map and fold and so on to compose these proofs. So part of the development of Edinburgh LCF, they developed a meta language to write down these proofs in ML, it was simply called. Right. So meta language has had quite a career also outside of the field of theorem proving, so it's probably more famous now than Edinburgh LCF, I would say. So meta language went on to become a programming language in its own right, standard ML. Standard ML in turn has influenced many other programming languages like Haskell, probably Clojure as well, OCaml and so on. And it's influencing also Java now. I was teaching a Java course and it has all sorts of lovely functional features in it that wasn't there when I was a student. So that's nice to see. In the slightly more small-scale world of automated theorem proving, Edinburgh LCF was very influential as well. So there are many systems which maybe some of you have heard of, like Isabelle Hall, Coq, Hollite, which Isabelle I use in my work, for instance. There's also one system which should be here on the slide called ACL2, which reasons in a Lisp-like language. So, okay, if we take a little break from the history lesson here, I think these interactive systems are actually quite nice examples of humans and machines collaborating. So computers are very good at keeping track of fine details. They don't get bored, they don't take shortcuts, they don't get tired, they're not sloppy, and they don't make silly mistakes, right? Humans, on the other hand, we're quite good at things like doing the creative part, so thinking outside of the box, or coming up with new theories, extending our languages, doing analogies, introducing new definitions, and so on. And this is quite important. I think this is somewhere where computers really complement us humans. Anyway, back to the history lesson. So we've come to the 1990s and noughties. So by this point, these interactive theorem provers are quite well developed. Quite a lot of mathematics have been formalized, that is programmed in these systems. There's a lot of proof checked. So they now have quite a large bank of knowledge that you can build on that the systems can use. So they've learned something in some sense. There's also some famous examples where people try to formalize famous historical proofs. So one example is Jacques Fleuriot's PhD thesis from '98. He was one of my teachers. He formalized Newton's Principia in this Isabelle system that I mentioned. And he did actually find a small error which had been undiscovered for 300 years, which he corrected. It wasn't, gravity still worked and so on, but nevertheless, even Newton made errors. And also one of my favorite examples, which is Kepler's conjecture, that was proved by Thomas Hales in '98. So Kepler's conjecture was kind of one of these great unsolved problems of mathematics for several hundred years. It was stated initially in 1611. And it conjectured that the most efficient way of stacking spherical objects, for instance cannonballs, is to put them in a pyramid. And this was not some strange problem of interest as a curiosity. This was very relevant. This was, Queen Elizabeth sent out buccaneers on the seas to chase down the French ships. And it was very important to have enough cannonballs, right? So she had some mathematicians at her court, and one of them was corresponding with Johannes Kepler, and he started thinking about this, but he didn't solve it. So 400 years later, Thomas Hales presented this proof, 300 pages, 50,000 lines of code. So why was this so big? Well, there was some sort of massive case split in this proof that you couldn't get rid of, because you need to exclude all the possible counterexamples, which was a finite number that had been proved before. So Hales submitted his paper, like all academics do, and then he waited. And if you're an academic, sometimes you have to wait for reviews for a long time. It's really annoying. But Hales had to wait for 4 years. Then they got back. And then they said that, we're quite sure that this is okay, but we really can check all these computer calculations, so we're not 100% really. And Hales wasn't happy. He's a mathematician. They deal with certainty. So he actually launched a project called Spec to formalize in Proof Assistant all this 50,000 lines of code and verify it, check it by the computer. He didn't want to have any silly mistakes like Newton or... So, this was quite a big project. It went on for 9 years. The final paper, they succeeded. The final paper had 22 authors and had given rise to 5 PhD theses on the way. So it was a lot of work, but they did it. And now everyone is pretty certain that, yes, if you're going out on your ship, stack your cannonballs in a pyramid. Right. Today, where are we today? In relation to Newell Simon's dream of having computers discover and prove an important mathematical theorem. Well, not quite there. So they've proved important mathematical theorems, but they haven't discovered and done it automatically, really. So computers are, today they're a lot faster, of course, than in the 60s and 70s. So these basic algorithms that were developed then are now quite powerful, and people have tuned these heuristics. So this kind of reasoning as search can do a lot more today than it could in the 60s and 70s. So, for instance, a few years ago, there was an open problem in mathematics, the Boolean Pythagorean triples problem, which was proved automatically, no human involvement, by one of these SAT solvers. So this was in propositional logic. You only have true and false. The proof was 200 terabytes. So, but apparently there are statements in mathematics where you don't get away with smaller proofs. So 200 terabytes or nothing, then, well, take it or leave it. But this is very impressive, right? I don't think you could have done it without automated reasoning. Nowadays, another important tool is they're often called hammers. So we have these interactive provers that I talked about, where they can do the easy bits themselves, but the humans have to do the hard bits. But now we have connected them to automated provers. So larger and larger chunks of proofs can actually be done automatically. There's a little bit of machine learning. This is one of the few parts in my talk where I have machine learning. So you remember you have these huge libraries of facts. So they've proved a lot of things. How do I know which ones are relevant? So I don't want to swap my automated reasoning systems because, well, they're better than in the 70s, but if I give them everything I know about mathematics, they will still fall over. So this bit of machine learning there, trying to figure out, well, have I seen something similar? What are the similar facts? Pretty basic machine learning, but nevertheless. And select some relevant facts, give it to one of these automated systems that does reasoning as search. And then it comes back and says yes, and then the interactive prover have to try and recreate the proof because it doesn't trust this external system. But this works pretty well, and this was actually used quite extensively in the Spec project. So there's this, we're getting more automation, slowly but surely. Okay, so what's still missing from this statement of Newell and Simon? Well, we can do proofs that are too large for humans, but the creativity somehow still comes from a human to tell it what to go and prove. So, and it also relies on having some building blocks to play with. But what about if we start some new mathematical theorem? We could invent a new data type, for instance, in a program, and we want to run some functions on it, and we want to find out what properties does it have. So that's what I'm interested in my research. So I'm going to do a small demo of a system that we're developing at Chalmers. It's called Hipster. And I'm going to ask it to automate a homework assignment that I like to give third-year students at the University of Edinburgh a few years ago. And they were in a course of functional programming. And I tell you, when I was an undergraduate, this took me quite a while to prove. You had to come up with lemmas, and you had to do induction. And then I saved this assignment, because I finally solved it. I was very happy. I got an A on the course. But I saved this assignment, because then I started working as a PhD student on theorem proving. And I thought, well, this would be nice if I could get it done automatically. So I'm going to try and show you a little demo. Bear with me when I'm rearranging the displays so I can see it myself. Okay. So this is this little program. So now I'm actually running one of these systems, Isabelle Hall. So for our intents and purposes, it's kind of like a functional programming language with some facilities for doing mathematical proofs about these functions. So here is like a really simple sorting algorithm, insertion sort. And we also have a function sorted there, or predicate sorted, which tells you if a list is sorted or not. We have an insertion function, and we have an insertion sort function. Very simple. So here's my homework. I've been asked to prove if insertion sort produces a sorted list, standard homework assignment. I'm throwing Sledgehammer. This is like the best automated tool in this Isabelle system. and it times out. It calls like Vampire, CVC4, their external system. These systems wins prizes. Times out. Can't do it. Okay. So now I'm going to cheat on my homework. So I'm going to call this system called Hipster that we have developed. It's going to take about 3 minutes. In the meantime, I hope to explain how it works. So I've given it 3 arguments. That's the 3 functions that I wanted to discover properties about. So Hipster actually collaborates with an external system called Quickesse, which is written in Haskell, which does a lot of testing. So actually, it's already come up with a bunch of conjectures which it thinks are true about this program. So that took a few seconds. Now it's going to spend a few minutes trying to prove them. So, right. While it does that, I'm going to give you a quick tour. So, what's happened behind the scenes is that Hipster has translated this program in Isabelle to Haskell. So we have a Haskell program. In Haskell, it's been passed to this system called Quickesse, not to be confused with Quickcheck, which it uses. Quickesse starts building up terms like a puzzle. So using the function sorted, insertion sort, and insert, and the constructors from the list type, so the empty list and the cons. What sort of type-correct terms can I build? And it builds loads of those. OK, what am I going to do with all of these? Well, I do have a wonderful tool called Quickcheck in Haskell. That's a property-based testing system. So what Quickcheck does really well is to generate values of these types. So it can generate a lot of random lists. Okay? You can plug these random values into our terms. Our terms contains variables. And then you can evaluate them. And then you can see which ones of the terms that evaluates to the same value. Very simple. So this way, you put all your terms in a big pile, an equivalence class, candidate equivalence class, and then you start evaluating them on random values. And all the ones that evaluate to the same value, you put aside. Those that are different, you put in a different pile. And then you repeat this. And it doesn't take very long. It's already spat out some conjectures. And it creates, from these equivalence classes, it conjectures a bunch of equations. Some of them are not very interesting because they are actually like the definitions again. So Quickesse doesn't know what the definitions are. It just tests them blindly, treats it as a black box. And now I think it's done. Let's see. Woo. Here it's, let me put the output in there. And anyway, after it's done that, it gives them back to Isabelle, and Isabelle tries to prove them automatically. So I haven't done anything here. I've been talking, and my system has been doing loads of maths. It's come up with a bunch of lemmas. It's done some induction. It used some particular induction rules, some simplification. Anyway, let's look what happens to my homework now. That was what we were interested in. Aha! It finds a proof, and I can paste that in. I tell you, I mean, even if we had to wait a while, it took a lot longer for me to do this proof when I was a student, hours. So, what does this proof mean then? It said simp add lemma AD. So obviously it proved some important lemma that they named lemma AD. Let's look at that. Well, this is actually, it's the same thing, right? It's just prefixed it by the name of my file. So this is the actual proof. I didn't tell it that this was what I was trying to prove. It rediscovered it and said, this is an interesting property. So I prove it for you. And, well, it used induction. It used a particular induction rule, which is following the recursive structure of the insertion sort function, if anyone's interested. It did some simplification. And then at the final step, it applied another lemma. So let's look at what that lemma is. That's our key lemma. So this is the key lemma that you need to prove that insertion sort produces a sorted list. Namely, if you have a sorted list Y, then if you insert some element X into it, it's still a sorted list. And that's our key lemma that it came up with. Came up with it, proved it completely on its own. It also discovered a bunch of other properties, which are, this one is not so nice. It's kind of the implication the other way around. Actually, it discovered these two AA and AB together. So it just decided to present them as two. Discovered some other things about inserting into a list as a nice bonus. Yeah, it discovered our homework assignment and a few more things. Not too many. It's manageable. And it's got rid of a lot of boring things as well. So I mentioned that it actually rediscovered some of the definitions of my function, but I already know them, so it got rid of those. OK, so I'm going to go back to my presentation, I think. So that's how we automate our homework. I think I will have to skip this second demo. I might do an encore if we have time. But it's quite interesting to use this also if you have a buggy program and see what it comes up with. So this is something that, well, if I made a mistake in my code, what does Quickspec come up with? If you have an idea of what your program should do and you get properties which doesn't agree with that, then perhaps that's indicative of a bug. But I think I might not have time for that, or no. Anyway, so this is what you saw. We started in this green box. That was what was on the screen all the time. That was our functions. Those, when I typed in Hipster, were translated to the world of Haskell. That's those pink boxes. And Quickspec was the system that generated a bunch of terms. Then it started testing them using random values from QuickCheck. Dividing them up in equivalence classes, spat out a bunch of conjectures. That's our yellow box. Sent them back into Isabelle. And Isabelle actually had, you don't see that in the demo, but what's actually happening is that you have a two-stage process. So one is easy reasoning. So if something is too easy to prove, then Hipster says, well, it's probably not worth giving to the human. The human is probably not interested in this. So it throws it away. Then it has a second phase, which I call hard reasoning. And in this case, it's a parameter to the system. In this case, I let hard reasoning be proofs by induction. Because if you need induction, then it's maybe worth showing to the human. But it might be the case that the reason why this actually took 3 minutes and didn't just go through it once was that sometimes it tries to prove some of these conjectures in the wrong order. And it needs to use, as you saw, some of the other ones as lemmas. So it builds up its knowledge base. It kind of learns things about these functions, this language. And as it does so, it becomes kind of more powerful, and it becomes better at doing proofs. So if I fail the first time, I just put it back. I put it to the side and say, OK, I'll wait with that. I'll try to prove some other things. And I'll get back to it later on. And then it retries it. And maybe it's proved an important lemma in the meantime. And all of a sudden, it works out. It proves it. It puts it back in its theory. It's learned some new facts on its own that it's discovered. So this is kind of Hipster is well, it's an academic system, but at least, well, we're getting a little bit more of this quote by Newell and Simon. So, well, within 10 years, we've gotten that part already. That was 58, so we're way past that. But we have discovered automatically and proved maybe not important or new theorems, but nevertheless homework assignment theorems for university students. So that's pretty good. Still some way to go, but I think it's an important step in getting this whole statement. So finally, what will happen in the future? You're getting a lot more mathematics digitalized in large proof libraries. I've hinted a little bit at, well, doing theorem proving is a bit like a game. You do have rules. You have the rules of logic, you have the rules of resolution, and so on. So it's a little bit like a game. So what's starting to happening now is, for instance, that people are trying to experiment with things like reinforcement learning. So just letting the prover go away, maybe not only discover things, but figuring out what's the most efficient way of proving them as well. So there's a system called Holist, which is developed by some people at Google, which is very interesting. So maybe we'll have mathematical assistants which can actually sit and learn and figure out what is the most productive next step to take in a proof. Maybe then we can actually get these important and new proofs as well. Still early days, many open questions. There are many subtle differences between a game like chess or Go and mathematics. But we'll see. Reasoning by analogy is another interesting venue. Humans can do, well, this is a little bit like that theory I saw over there. Maybe I can translate it into this, and then I can do the reasoning here because it's easier. You've seen maybe this word to vec, where you say, you translate words in natural language to vectors. And if you do this embedding really well, you can discover interesting analogies. So can we do something similar to that in mathematics? And there are both similarities and differences between natural languages and mathematical languages, which I'd be happy to discuss in the break or something. So yeah, there's interesting things coming as well. If you want to try a piece of experimental academic software, Hipster is available on GitHub. Quickesse, if you're a Haskell programmer and you just want to try the Haskell part, you don't get the nice proofs, but you get the nice equations that you can look at. You can try Quickesse as a Haskell package, standalone. And finally, I think I left enough time for some questions. But before that, I would like to thank some of my contributors and collaborators, Nick, Koen, Irene, Solrun, Max, Dan, and Johannes, who've contributed to various parts of this project. It would not have been possible without them. So, thank you very much.
Are there any questions? Yeah.
Who proves that provers are correct.
Ah. What happened now? That, of course, is it's the question. So there has been some projects where people have tried to prove their interactive theorem provers correct. So, for instance, in the whole light system, which is one of these provers, they've actually done that. But in general, you know, it's very hard to prove the entire stack down to the compiler and so on. There is work on that. I don't know if you've heard of CakeML. No? So there is a dialect of ML called CakeML, which is developed by my colleague Magnus Myrén and his group, where you prove all the steps in the compiler. So if you then go and implement a theorem prover in CakeML, it's verified all the way down to the compiler. What's a little bit more done today is that you have in these systems, you have a small core of basic inference rules, which you test very well, you stare at it for very long, and you try to make certain that this core is actually working. And then all the proofs have to go through this logical core. So you can be pretty high confidence that it's actually working as intended. Does that answer your question? Thanks.
Thanks, that was really interesting. Do you know what the practical differences are between the different theorem provers for different working, what you want to do? So what should I use? Should I use Isabelle or Cog or whatever?
I think it mainly depends on what libraries you need to some extent. And I mean, sometimes some people do have preferences as to the meta logic of the provers, which they're all higher order logics with subtle differences. And some people are very concerned about, should I have the law of the excluded middle or not? Is it classical logic or? So then maybe if you're okay with classical logic, you choose Isabelle. If you're intrinsic logic, then you choose Coq. If you're French, you choose Coq. I mean, they're all similar. They have different user interfaces, so it's a little bit depends on what you prefer. Some of them are low level. Isabelle has got quite a fancy user interface, so.
Is there any hope for machine learning to explain its reasoning?
That's a really interesting research question right now in the AI community, explainable AI. I think there is. I mean, it depends a lot on which algorithms you use. I mean, some machine learning algorithms already today, you can argue that they are interpretable. So, like, the more sort of linear models, they discover functions. Whereas really, really deep neural networks, well, there are techniques where you try to sort of slice them and query the layers and look at these layers. Maybe it's discovered something about horizontal lines or faces. So I think there's hope, but we're not there yet. And I'm not going to say that we'll be doing that in 10 years. It might take a lot longer. But I think there's hope.
Hi. You said that if it's too trivial, don't show it to the human.
Yes.
If it's interesting, show it to the human. But what if it's important and the AI decides not to show it to the human?
If it's important and it decides not to show it to the humans, well, that's bad. So it doesn't do that too much. Usually because the way I configured it in this demo is that it doesn't have a very powerful automation in this trivial step. So, but certainly if I give it a slightly more powerful reasoning capabilities in the trivial step, that might happen. And that's not so good, of course. so that's a bit of a, yeah, you have a bit of a slider there. How much are you going to keep and not? Yeah. What do you consider? What do you mean by trivial? It's going to be a little bit up to the user.
Hello. I'm going to be a cliche and say this is not a question, but more of a comment. And if somebody was inspired by this proving stuff and is interested in like computer mathematics, there's a new book out called The Little Typer, which takes you kind of through the first steps of how you can prove things kind of in a programming language. So that's a very nice place to get started if you're interested in all this, but it seems unapproachable.
So has anybody tried to use genetic algorithms in coming up with theorems to test?
Not that I can think of now. Probably someone has tried, but not to great success, I would say. Genetic algorithms have fallen a bit out of fashion, so I guess they were used a lot some 20 years ago or something. But I mean, there's certainly, you could imagine things influenced by mutation testing or something to try, but I don't think it's been used to any great success. But I think people have tried.